Welcome back to the Quantum Slumber. I'm glad you're here tonight. Imagine you wake up tomorrow morning, reach for your coffee cup, and for a split second, you see it differently. Not as ceramic and warmth, not as habit and comfort, but as a kind of cosmic contradiction. Because every atom in that cup, every molecule in the water you sip, every bit of calcium in your teeth, iron in your blood, carbon in your brain, was once not here. Not almost not here. Literally not here. Right now, as you listen, you're surrounded by something like 10 to the 80 power atoms, an ocean of building blocks so vast your mind can't hold it all at once. And yet, if you roll the clock back far enough, back to the young universe, back to the beginning of our story, there was a time when not one of these atoms existed, not a single one. That's the sentence that feels impossible to say out loud. The universe had to learn how to make matter from nothing. And tonight, we're going to follow that learning process, slowly, gently, like tracing a fingerprint across time. We'll move in 4 smooth steps. First, back to an era where atom was a meaningless word, when the universe was pure energy, and the forces of nature were still finding their shape. Then we'll watch the first durable ingredients appear. Protons, neutrons, electrons, like the first letters of an alphabet reality hadn't learned to speak yet. After that, we'll arrive at one of the most beautiful turning points in cosmic history, the moment the fog finally lifted, when the first neutral atoms formed and light was set free, leaving behind a faint glow we can still detect today. And finally, we'll follow the long climb from simple atoms to blazing stars, from stars to heavier elements, and from those elements to something astonishingly personal. You, a living arrangement of ancient matter, thinking about its own beginning. Because nothing doesn't mean empty the way a room is empty. It means no atoms, no chemistry, no cups, no lungs drawing breath, no eyes to witness light. Just a reality so hot and dense that even the idea of an atom couldn't survive, like trying to describe snowflakes inside a furnace. Before we begin, leave a quick comment and tell me where you're listening from and what time it is in your corner of the world. And if you'd like more calm, science-filled journeys like this, stories that make the universe feel vast and somehow personal, feel free to tap, like, and subscribe. Now, let's start with the simplest, most unsettling question of all. How did everything get here from nothing? When most people hear the word atom, they picture something simple, a tiny hard bead, a microscopic marble, a little dot that sits at the bottom of reality like a brick in a wall. But that picture is one of the oldest illusions in science. An atom isn't a solid thing so much as a shape of possibility, a pattern that keeps repeating itself so reliably that your brain calls it matter and moves on. If you could take a single atom and scale it up until it was the size of a football stadium, the nucleus, the heavy central core, would be smaller than a marble placed right on the 50-yard line. Everything else you think of as the atom, the space where the electrons live, would fill the entire stadium. The seats, the lights, the air above it, the open sky. So, when you touch your coffee cup and feel something firm and unshakable, you're not feeling solid stuff packed tightly together. You're feeling forces, rules, an invisible choreography that makes emptiness behave like substance. At the center is the nucleus, a tight bundle of protons and neutrons. Protons carry positive charge, and if you've ever played with magnets, you already know the problem. Like charges don't like each other. Protons should repel, they should push apart. By ordinary intuition, the nucleus should fly to pieces instantly, but it doesn't. Because the universe has a second kind of glue, one that doesn't exist in our everyday experience. The strong nuclear force. At the tiny distances inside a nucleus, it's overwhelmingly dominant, roughly 100 times stronger than electromagnetism at that scale. Strong enough to overpower the proton's natural urge to separate and hold the nucleus together like a clenched fist. And it has a strange personality. Most forces weaken as you pull things apart. Gravity fades with distance. magnetism fades with distance. But the strong force behaves almost like the universe has a stubborn rule about intimacy. The more you try to separate the pieces, the more the force resists, until it becomes energetically easier to create new particles than to allow quarks to be alone. Nature, in a deep sense, refuses isolation at the most fundamental level. Now around that nucleus, we meet the part that breaks people's intuition most gently and most completely: the electrons. If you learned atoms in school, you probably saw a little solar system diagram, electrons orbiting like planets around a sun. It's a convenient picture, and it's not totally useless. But it's not what's really happening. Electrons don't fly around the nucleus in neat little loops. They don't have a track. They don't have a lane. What they have is a probability cloud, a region of space where the electron might be found if you looked. It's less like a planet and more like a fog bank. Less like an object, and more like a rule about where an object is allowed to appear when reality demands an answer. And that's the first place the word quantum stops being an abstract label and becomes a physical fact. Because classical physics, the physics your intuition is built from, predicts something disastrous. A negatively charged electron should be attracted to the positively charged nucleus. It should spiral inward, radiating away energy, collapsing the atom in a heartbeat. Matter should be impossible. Chemistry should never get off the ground. And yet atoms are stable. Your coffee cup survives the night. Your body holds its shape. The world stays put. Quantum mechanics makes that stability possible by introducing a strange constraint that feels almost like cosmic etiquette. Electrons are only allowed to exist in certain energy states, discrete levels. Not a smooth slide downward, but steps. Allowed shelves in reality. An electron can't simply choose to sit closer and closer until it merges with the nucleus, because between those allowed levels there is nothing it can occupy. The lowest level, the ground state, isn't a compromise. It's a locked-in arrangement, a stable balance between attraction and motion, where the electron cannot fall any lower because lower is not permitted. This is one of the quiet miracles of existence. Matter endures not because the universe is sturdy and simple, but because the universe is restricted in just the right way. And once electrons are held in these quantized patterns, something else becomes possible. Atoms can meet each other and share their outer electrons in controlled ways. They can link. They can form molecules. They can build chains and lattices and spirals and membranes. The same electromagnetic force that tries to pull electrons toward nuclei becomes the force that allows atoms to connect into chemistry. It's worth pausing on what that means. Everything you call real in daily life, wood, glass, skin, bone, air, depends on a tiny set of rules that keep repeating. A dense nucleus held together by the strong force, electrons living as probability patterns, and quantized states that prevent collapse. And here's the deeper twist, one that quietly sets up everything that comes next. These rules don't merely describe what atoms do once they exist. They are the reason atoms can exist at all. They are the reason the universe is capable of building stable structure instead of dissolving back into featureless energy. So, when we talk about atoms being born, we're not talking about tiny marbles appearing in space. We're talking about the universe discovering a stable arrangement, an architecture, where emptiness can behave like substance, where energy can condense into enduring patterns, and where those patterns can persist long enough to become cups, oceans, bones, and minds that can wonder how any of it ever began. There's a sentence that sounds simple until you try to say it out loud in a serious way. Everything came from nothing. In everyday life, nothing is just a pause between things. An empty cup before you pour coffee. A quiet room before someone speaks. A blank page before a story begins. Even then, it isn't truly nothing. The cup is still there. The room is still full of air. The page is still paper, still atoms, still history. But when we talk about the beginning of the universe, we're using nothing in a far stranger, more demanding way. Not an empty space, not a dark room, not a vacuum inside a glass jar. We mean no atoms, no molecules, no dust, no oxygen waiting politely in the corner, no carbon hiding in the shadows, no protons, no electrons, no chemistry, no stuff at all. And that's where the story becomes almost uncomfortable, because your mind is built to imagine rearrangements, not origins. We can picture wood becoming ash, water becoming steam, a star becoming a cloud of gas. But imagining matter itself arriving for the first time feels like trying to picture a color you've never seen. Here's the subtle twist that keeps this from becoming a purely philosophical riddle. Physics doesn't begin with matter. It begins with rules, relationships, patterns that can exist even when there's no familiar material to carry them. Modern physics treats the world less like a pile of tiny objects and more like an interlocking system of fields and energies, where particles are what you get when those fields ripple in certain stable ways. So, when we say from nothing, what we're really doing is pointing at a boundary, the moment where our everyday categories, solid, liquid, object, ingredient, stop being useful, and we have to speak in a different language. A universe that is too hot, too compressed, too young for atoms is not an empty universe. It's a universe that hasn't cooled enough to let matter settle into structure. That's why this story isn't a magic trick. It's a cooling story, a settling story, a story about the universe going from wild and undifferentiated to stable and specific, like steam slowly becoming droplets, and droplets becoming something you can hold. And still, we shouldn't pretend the mystery isn't real. When we run the clock backward, our equations do something unnerving. They don't gently guide us to a clean starting line. They often rush toward a place where densities and temperatures shoot upward, and the math starts spitting out infinities. Numbers that don't behave like physical answers, but like warning signs. It's as if reality is telling us, you can follow the trail this far, but not all the way. So, scientists use careful language. Some talk about an early state we can describe without claiming it's the absolute beginning. Some talk about a quantum origin, where space-time itself may be part of the phenomenon, not the stage it happens on. Some talk about models where the universe emerges from a vacuum state, where empty doesn't mean nothing, but rather the lowest energy condition a set of fields can have. And if that sounds like we're moving the goalposts, it's because we are learning what the word nothing can and can't mean in physics. The vacuum of modern theory isn't a pure void. It's more like a quiet ocean with rules underneath it, stillness that can still contain tension, potential, structure waiting to be nudged. Which leads to the most important point for tonight. This isn't about getting a perfect answer to the ultimate question in a single breath. It's about understanding how the universe went from a state where atoms could not exist to a state where atoms became inevitable, almost unavoidable, the moment conditions allowed them. Because once the early universe had the right ingredients, once it had energy and expanding space and the right set of forces, matter wasn't added like a new object placed into a box. Matter was made possible by the way the rules unfolded. And in a sense, that's the most human way to understand from nothing. Not a magician pulling rabbits out of an empty hat, but a universe that begins as pure potential, and then, step by step, learns how to hold a shape. For a moment, let your mind do something it almost never does. Let it stop picturing things and start picturing conditions. Because in the earliest moments, the universe wasn't a place filled with objects. It was more like a rule book written in heat, so hot, so dense, so compressed, that the usual words we use for reality begin to feel too small. If you could rewind time far enough, you wouldn't find a tiny spark floating in empty darkness. You wouldn't find a little marble of matter sitting inside a larger room. You'd find something closer to a boundary, a limit, where our descriptions still work, but only barely. Physicists sometimes say the early universe was smaller than a period at the end of a sentence. That's not a measurement you can put on a ruler. It's a way of admitting that we're approaching an edge where common sense stops helping. And at that edge, the equations begin to behave strangely. They don't politely offer a neat origin story. They surge toward values that explode, temperatures that soar, densities that climb, curvatures that spike, until the math starts returning infinities, like a dashboard flashing warnings you can't ignore. That doesn't mean the universe was infinite in a literal way. It means our tools are reaching the end of what they can confidently say. So instead of pretending we can stand inside the first instant and describe it like a scene, scientists do something more careful. They focus on what happens after that unknown boundary, when the universe is already expanding, already cooling, already becoming something we can model. And the first clear theme of that era is surprisingly gentle. The universe is born hot, and then it spends a very long time relaxing, cooling, stretching, unfolding, becoming spacious enough for structure to appear. In those earliest fractions of a second, the universe is not just hot, it's hot in a way that melts distinctions. At energies that extreme, the forces of nature don't behave like separate personalities. They blur together, as if they were once the same force wearing different masks. Today, you know the cast: gravity pulling quietly from afar, electromagnetism making atoms and light possible, and the strong and weak nuclear forces operating in the tiny kingdom of particles. But early on, the universe may have been so energetic that these roles were not yet divided. The laws of physics, in a sense, were still in a more symmetric state, simpler in one way, yet too intense for anything stable to form. Then comes one of the strangest ideas in modern cosmology, an idea that sounds like science fiction until you realize it's proposed to explain very specific features of the cosmos we actually see: inflation. Inflation is the claim that very early the universe went through an episode of violent, exponential expansion, not matter flying through space, but space itself stretching, fast, enormously fast. So fast that distances between points can grow faster than light can cross them without breaking relativity. Because relativity limits how fast information moves through space, not how fast space can expand. It's a subtle distinction, and it matters. Imagine a pattern drawn on a rubber sheet. If you pull the sheet apart quickly, two dots on that pattern can separate faster than any ant could crawl, because the sheet is doing the moving. The dots aren't racing. The stage is stretching. Inflation, if it happened, would have done two almost poetic things at once. First, it would have made the universe astonishingly large, astonishingly quickly, smoothing it out like tugging wrinkles from a blanket. Second, it would have taken tiny quantum-scale fluctuations, microscopic variations that are normally confined to the smallest scales, and stretched them across cosmic distances, planting the faint seeds that gravity will later grow into galaxies. That last part is the kind of twist that feels like a signature move in a viral science story. The idea that the largest structures in the universe may have begun as the tiniest quantum whispers. But even here, there's something important to keep grounded. Inflation is strongly supported by how well it explains certain observations, like why the universe looks so uniform on large scales, and why its geometry appears so close to flat. Yet the exact mechanism, what field drove it, how it began, how it ended, is still an active area of research. And that's okay. The competitor style we're matching doesn't pretend the unknown parts aren't there. It uses them as the right kind of wonder, mystery with boundaries. After inflation ends, if it did, what follows is often described as reheating, where the energy associated with that inflationary state transforms into a hot soup of particles and radiation. The universe becomes filled with energy dense enough to create particles in a kind of restless equilibrium, matter appearing and disappearing, not as stable atoms, but as fleeting possibilities. And as it cools, another profound event likely happens. The forces begin to separate into the distinct behaviors we recognize today. One of the most famous splits is the electro-weak transition. The idea that electromagnetism and the weak nuclear force were once unified and then became different as the universe expanded and temperatures dropped. If that sounds abstract, here's a more human way to picture it. It's like a single white beam of light passing through a prism. The colors were always in there, but only under the right conditions do they separate into their recognizable forms. In the early universe, symmetry is that white beam. Cooling is the prism, and the laws of physics begin to show their individual colors. This separation matters because it's the universe gaining architecture. The rulebook becomes more detailed. The possibilities become more specific. Certain reactions become favored. Certain particles become stable. Certain patterns stop being temporary and start becoming the building blocks of everything that will come later. And still, despite all this grandeur, there's a quiet, almost haunting detail. At this stage, there are no atoms, not even close. There is no nucleus for an electron to orbit, no stable neutral structure that could resemble the matter you know. The universe is still too energetic, too chaotic, too young for that kind of order. It is a place where the rules are being defined in real time, and where energy dominates like an ocean at storm level. Endless motion, endless collisions, endless transformation. And if you hold that image for a second, if you let it sit gently in your mind, you can feel the tension that drives the story forward. Because atoms are not a default. They are an achievement. They require the universe to cool enough, expand enough, and settle enough for stable pieces to exist, long enough to meet, combine, and endure. And we're getting close to the moment when the first truly durable ingredients of matter will begin to appear. Not atoms yet, but something like their bones. Still, no protons, no neutrons, not yet. There's a point in this story where the universe stops being a pure idea. Hot equations expanding space, forces choosing their identities, and starts trying to assemble something that can last. Not atoms yet, not even close. But the ingredients of atoms begin to appear in a form that feels almost physical, like the first bones of matter. Imagine conditions so extreme that solid and liquid and gas aren't even wrong, they're irrelevant. In these early moments, the universe is a furnace without walls. Energy is everywhere, and that energy keeps turning into particles, and those particles keep dissolving back into energy, as casually as breath on a cold window. This is what scientists call a quark-gluon plasma. It sounds technical, but the concept is simple in a strangely comforting way. Before protons and neutrons could exist, their smaller pieces, quarks, were not yet locked into stable partnerships. They moved in a dense, seething crowd, held together by the strong force's messengers, the gluons, in a state that is less like building blocks and more like molten potential. If you want a human image for it, picture trying to build a house in a tornado made of fire. You can have all the lumber you want. You can have nails, you can have blueprints, but if the wind is violent enough, nothing stays together long enough to become a structure. That's the early universe here. Everything present, nothing settled, and yet something quietly inevitable is happening in the background. The universe is expanding, and expansion in cosmology is the gentle king of time. As the universe expands, it cools, not because heat escapes into a surrounding space, there isn't an outside, but because the energy spreads out. The same amount of energy gets diluted into a larger and larger volume. Cooling changes the rules of what can stick. At high enough temperatures, quarks behave like free agents. They can roam in a kind of collective fluid, constantly interacting, constantly exchanging gluons, constantly reshuffling. But as the temperature drops, the strong force reveals one of its strangest traits, something that feels almost like personality. The strong force becomes stronger as you try to pull quarks apart. This is not how most forces behave in your everyday life. If you pull two magnets apart, the pull gets weaker. If you step away from a campfire, the heat fades. But the strong force is different. It's as if the universe is saying, I will allow you to move freely in the heat, but I will not allow you to be alone forever. Physicists call this confinement. Quarks can't be isolated. You don't get a single quark drifting through space like a lonely grain of sand. When you try to separate quarks, you pour energy into the system, and that energy tends to create new quark-antiquark pairs, snapping the strings into new combinations rather than letting one quark escape. It's not romance, it's not morality, it's simply how the strong force behaves. And in the cooling universe, that behavior becomes the turning point. somewhere around a tiny fraction of a second after the beginning, on the order of microseconds, the universe crosses a threshold often described as the QCD transition, when this free-flowing quark-gluon soup begins to freeze into composite particles. Not ice, not crystals, but into stable groupings, hadrons, the family that includes protons and neutrons. Here's what matters for our story. A proton is a specific arrangement of 3 quarks. A neutron is a specific arrangement of 3 quarks. Same basic ingredients, different recipe. And once the universe cools enough for those recipes to hold, you get something that feels like the first durable hardware of matter. Objects that can persist long enough to become part of larger structures. It's one of the most dramatic upgrades reality ever performs. Before, the universe is a storm where components cannot settle. After, the storm calms just enough for the first long-lived pieces to lock into place. If you pause on that for a second, it becomes oddly emotional, because this is where the universe first behaves like a builder, not just a blender. And the timing is wild. What we're talking about, this moment when quarks become bound into protons and neutrons, happens astonishingly early, long before stars, long before galaxies, long before light can travel across any meaningful cosmic distance. And yet, every time you touch a table or take a sip of water, you are interacting with the descendants of that transition. Every nucleus you've ever heard of begins with these 2 characters, protons and neutrons. But we should be careful with one subtle point, because this is where people often picture something too tidy. When protons and neutrons form, the universe still isn't a calm place. It's still incredibly hot. It's still filled with radiation. It's still swarming with particles that appear and disappear. These protons and neutrons don't instantly assemble into neat atomic nuclei the way your mind wants them to. They're born into chaos. They collide. They transform. Some neutrons decay if they don't find the right partners in time. What changes is not that the universe becomes peaceful. What changes is that the universe finally has pieces that can survive long enough to participate in a longer story. And you can feel the next tension building, even now, because protons and neutrons alone are not enough to make atoms. Atoms need electrons, yes, but more than that, atoms need coolness and time and conditions where charged particles can stop being torn apart by heat and light. So, we've reached a milestone, and also a kind of frustrating truth. The universe has learned how to make the bones of atoms, but atoms still can't exist. Not yet. Not in a stable, lasting way. And hovering just ahead is a mystery that feels almost like a cosmic accounting problem. An imbalance so small it sounds like a rounding error, and yet it determines whether anything exists at all. Because even with protons and neutrons arriving on the scene, the universe is still playing a deeper game. The game of why there is matter left over in the first place. For a moment, it sounds like the universe has finally found its footing. Protons, neutrons, the rough durable pieces that can survive longer than a blink. But then you notice something unsettling, something that doesn't feel like a detail, but like a verdict. Because those pieces shouldn't be here, not if the universe played fair. In the early cosmos, nature seems to have a preference for symmetry. Energy can turn into particles, and particles can turn back into energy. And when energy becomes matter, it often does it in mirrored pairs, one particle and one antiparticle, equal and opposite, an electron and a positron, a proton and an antiproton, a matching set, as if reality is balancing its own books in real time. If you could watch that era, it would look like a storm of creation and erasure, particles flashing into existence, colliding, and then, instantly, vanishing in bursts of light. Not like destruction in the dramatic sense, more like a constant canceling, a cosmic undo button being pressed over and over. And if symmetry were perfect, that's all the universe would ever do. Make pairs. Erase pairs. Leave behind nothing but radiation. No atoms, no chemistry, no stars, no hands to hold a warm mug, no eyes to close at the end of a long day. Just light thinning into an empty cooling expansion. So when you hear the next line, it lands like a quiet shock. Something went wrong. Or more accurately, something went slightly off balance. A difference so small it almost feels embarrassing to talk about. Like admitting your entire life exists because of a rounding error. But that tiny imperfection is the reason anything exists at all. Here's the idea, told the way it deserves to be told. Simple enough to feel it. Imagine, for a long stretch of time, the universe is making matter and antimatter in almost equal numbers. Let's say it makes 1 billion particles of matter and 1 billion particles of antimatter. They meet, they annihilate. They turn back into pure energy, mostly photons, like a cosmic flashbulb. Now imagine the universe does this again, and again, and again. But each time, it makes 1 extra particle of matter, not 1,000 extra, not 1 million, just 1. So you get 1 billion 1 particles of matter and 1 billion particles of antimatter. They annihilate in pairs until the antimatter is gone. And then, in the quiet after the storm, you're left with the leftovers. 1 particle in 1 billion. That's it. That's the miracle. Everything you've ever touched, every wall, every ocean, every bone in your body, built from the tiny remainder after the universe canceled itself out as completely as it almost could. When people say we're made of stardust, they're not even going back far enough. Before stars, before atoms, before even the first simple nuclei, there had to be this moment where reality chose more matter than antimatter by the slimmest possible margin. And what makes it even more haunting is that we don't fully know why it happened. We have strong hints. We have mechanisms that might do it. We have experiments that show nature is not perfectly symmetrical in certain ways. But the clean, satisfying explanation, where you could point to a single dial and say, "This is why we exist," still feels just out of reach. In physics, this puzzle has a name that sounds almost gentle: baryon asymmetry. Abaryons are the family that includes protons and neutrons. Asymmetry is the polite word for the universe broke its mirror. And there are rules, conditions really, that any explanation has to satisfy. The universe needed a way to create more matter than antimatter. It needed a way to treat matter and antimatter differently. And it needed a time when the cosmos wasn't in perfect equilibrium, so the imbalance could stick instead of immediately washing out. Scientists sometimes refer to these as the Sakharov conditions. You don't need to memorize that name tonight. What matters is the feeling behind it. The universe had to be a little unfair, not cruel, just biased by a whisper toward matter. And once you accept that, you start to see how strange the word nothing really is. Because if the early universe truly produced perfect symmetry, the story ends before it begins. No atoms ever form. Not because atoms are difficult, or because chemistry is complicated, or because stars take time, but because there would be no stuff left over to become anything. So, that 1 in a billion surplus becomes the seed of all future complexity. It's the reason the universe has substance. It's the reason there's a you to listen. Now, there's another detail people often miss, and it makes this even more vivid. The universe didn't start with matter neatly set aside in a safe container, protected from antimatter. Matter and antimatter were everywhere together, colliding constantly. The annihilation wasn't a one-time event. It was a long, relentless process, a cosmic thinning. The universe kept cooling and expanding, and as it did, the rate of collisions changed. The conditions shifted. Eventually, antimatter became rare because it was outnumbered, and because, when it met matter, it vanished. So, when you look out at the universe today and see almost no antimatter, what you're really seeing is the aftermath of a near-perfect cancellation. A universe that almost erased itself, and then didn't, by 1 extra particle per billion. That leftover, at first, would not have looked like atoms or molecules or anything remotely familiar. It would have looked like a hot soup of particles, still violent, still bright, still filled with light. But now it had something it didn't have before, a persistent inventory of matter, protons and neutrons that weren't destined to disappear completely. And that changes what the next few minutes of cosmic time can accomplish. Because once the universe has a stable supply of protons and neutrons, and once it cools just a little more, those leftovers can begin to do something that feels almost domestic. they can start finding partners. They can start forming the first simple nuclei. Not atoms yet, but the earliest hints of structure. And the strange thing is, the universe only gets a brief window to do it, because neutrons don't last forever on their own, and the cosmic temperature keeps dropping. So after this near total annihilation, after the billion-to-one miracle leaves the smallest remainder, the universe does what it always does with leftovers. It starts cooking. For a brief window of time, the universe becomes something surprisingly familiar. Not a place of stars or planets, those are still far away, but a place with rules, ingredients, and a ticking clock. A kitchen, in a sense. A hot, bright kitchen where the only things on the counter are the simplest building blocks nature can manage. By now, there's matter that actually stays matter. There are protons that don't immediately vanish, neutrons that can survive long enough to matter, and electrons drifting through the heat like loose sparks. But the universe is still unbelievably young. Not millions of years young, not even thousands. We're talking minutes. And in those first minutes, the cosmos tries to do something bold. It tries to assemble the very first nuclei, the cores of future atoms, before the conditions change and the opportunity slips away. This is the era called Big Bang nucleosynthesis. It sounds technical, but the feeling of it is simple. The universe is cooling, fast. Every second, the temperature drops, the pressure eases, and the frantic collisions become just a little less violent. But cooling here is still a kind of blazing. Matter is not quiet. Matter is a storm. In that storm, protons and neutrons are constantly being created, destroyed, swapped, and scattered. Early on, it's so hot and so energetic that protons and neutrons can transform into each other through weak interactions, almost like a reversible choice. But as expansion continues, the universe reaches a point where the temperature falls enough that those conversions slow down. The balance freezes out. From that moment, nature makes a decision it can't fully undo. There are more protons than neutrons, and the neutrons left on their own come with a quiet problem. A free neutron is unstable. Given enough time, it decays, turning into a proton, an electron, and a neutrino. It doesn't happen instantly, but it happens steadily, like sand slipping through a narrow crack. So now a cosmic timer starts, whether anyone asks for it or not. If the universe is going to build nuclei that require neutrons, like helium, it needs to do it before too many neutrons disappear. You can almost picture it. Protons everywhere, stubborn and durable, neutrons fewer and fading. And then the universe tries its first real construction project. The most natural step would seem simple. One proton meets one neutron. They bind. They become deuterium, a heavy form of hydrogen, a nucleus with one proton and one neutron. It's the smallest team that can lead to something bigger. And yet, for a while, the universe can't hold on to deuterium at all. Because even though it's cooling, it's still filled with incredibly energetic photons, particles of light so hot and so plentiful that they can smash fragile newborn nuclei apart the moment they form. This is the famous deuterium bottleneck. It's one of those moments in cosmology that feels almost emotional because it's so close to working, and yet it keeps failing. The universe keeps trying to take its first step, and light keeps undoing it. A proton and neutron manage to bind, only to be shattered again, over and over, a cosmic thread being pulled apart as quickly as it's woven. So, the universe has to wait, and it does something the universe is very good at. It keeps expanding until the temperature drops just enough that those destructive photons lose their edge, until there are fewer photons energetic enough to break deuterium, until the first fragile nucleus can finally survive long enough to meet another. And when that happens, when the bottleneck opens, everything accelerates. Because once deuterium can persist, it becomes a gateway. Deuterium can collide with a proton and form helium-3. Deuterium can collide with another deuterium and form helium-4. Helium-3 can capture another neutron or proton and move up the chain. The universe starts assembling helium the way a tide starts rising, slow at first, then suddenly obvious. And helium-4 is the prize. 2 protons, 2 neutrons. A tightly bound nucleus, stable and stubborn, like a small safe built out of the strongest early materials available. Helium-4 is so stable that once it forms, it tends to stay formed. The universe likes it. The physics favors it. So, a great portion of the available neutrons get locked away inside helium-4 nuclei, because that's the most secure place they can be before they decay. It's a strange kind of salvation, neutrons escaping their own instability by becoming part of something sturdier. But even in this triumphant moment, the universe remains limited. It can't build much beyond helium. Why? Because the early universe is expanding and cooling too quickly, and because there's a famous problem with nuclear building blocks. Nature doesn't offer a stable nucleus with 5 particles, and it doesn't offer a stable nucleus with 8. Those gaps matter. They create a kind of missing rung on the ladder. In stars later, gravity compresses matter for millions of years and gives nuclear reactions the time and density to find clever pathways around those gaps. But here, in the first minutes, the universe doesn't have patience yet. It doesn't have the slow pressure of a star. It has momentum, it has expansion, it has a rapidly closing window. So, Big Bang nucleosynthesis makes mostly what it can make quickly. Now hydrogen nuclei, single protons, in overwhelming abundance. Helium nuclei, mostly helium-4, as the main second product, and a sprinkling of rarer leftovers like deuterium, helium-3, and a trace of lithium. That's it. No carbon, no oxygen, no nitrogen, none of the elements that later become soil, oceans, or cells. At this stage, the periodic table is barely a whisper. And yet, what the universe does make is stunningly important. Because we can check it. This is one of the most satisfying parts of the whole story. Big Bang nucleosynthesis is not just an idea we tell because it sounds elegant. It makes specific predictions about how much hydrogen and helium the universe should contain, and how much deuterium should remain. And when astronomers look at ancient gas clouds and the chemistry of the early cosmos, they find something astonishingly close to what the theory says. Roughly 3/4 hydrogen by mass, roughly 1/4 helium by mass, with small traces of deuterium and lithium that fit into the same picture. It's like discovering an old recipe card on the floor of the universe and realizing the measurements match what's still sitting in the pantry billions of years later. So, in a sense, this is a victory. The universe has built its first nuclei. It has created the raw inventory that will later feed stars, fuel fusion, and begin the long climb toward complexity. But there's an important detail that keeps this moment from feeling complete. Because even now, after nuclei exist, atoms still do not. The universe is still far too hot. Electrons are still moving too fast to settle down around nuclei. Photons are still too energetic, constantly knocking electrons loose. Every attempt at forming a neutral atom is immediately undone, like trying to write your name in sand while the wind is still screaming. So, what exists is a charged plasma, nuclei and electrons, separate, mixed, restless. The universe has cores, but no shells. Ingredients, but not yet the finished structure we'd recognize as matter. And it leaves you with a quiet kind of anticipation. Because once you understand this, you realize something beautiful and strange. The universe had to build the centers of atoms first, and then wait, much longer than you'd expect, for the rest of the atom to finally arrive. So, in these first minutes, the cosmos completes its earliest round of creation, hydrogen and helium, the simplest, most essential nuclei. And then it moves into a long, glowing era, where the pieces exist, but they can't yet lock together into the calm, neutral form that will one day fill the dark with stars. There's a strange point in the story of the universe where almost everything that matters already exists, and yet nothing can truly be seen. The ingredients are here: hydrogen nuclei, helium nuclei, electrons roaming free, light flooding space in unimaginable numbers. But the universe still behaves like a room filled with smoke. Not because there's dust or ash, there aren't even stars yet, but because of something simpler and more fundamental: charged particles. In this era, the universe is a hot plasma, a restless mix of nuclei and electrons that refuse to settle down together. And as long as those electrons remain free, light cannot travel in a straight, quiet line for very long. A photon tries to move forward and immediately runs into an electron. It scatters. It changes direction. It loses any clear sense of going somewhere. Then it scatters again, and again, and again. So, even if you could somehow stand in this young universe, if you could float in it, somehow protected, you wouldn't see stars, or darkness, or a sky. You wouldn't even see your own hand, because there is no seeing in the way we mean it. Light cannot deliver a clean message from one place to another. Space is filled with light, but it's trapped in a constant pinball game, bouncing off electrons like 1,000 tiny mirrors that never stop moving. This is why cosmologists call it the opaque universe, or more poetically, the cosmic fog. And it's a fog made out of physics. When we say fog, we usually mean water droplets, little spheres that scatter light. Here, it's free electrons doing the same job. The effect is similar. The universe becomes its own curtain. It's a strange thought, because if you rewind your mind to the beginning, you might imagine the early cosmos as bright and clear, like a clean explosion in an empty room. But the reality is more intimate and more claustrophobic. It's bright, yes, blindingly bright, and closed. Light is not racing freely into the distance yet. It's living inside the matter. It's stuck inside the soup. And this matters because it means the universe is holding on to a secret made of photons, ancient light that cannot escape until the right moment. If you've ever been driving through a thick morning mist, you know the feeling. Your headlights don't reveal the world, they reveal the fog itself. The light doesn't go out and bring back information. It just reflects and scatters and turns the air into a glowing wall. That's what the universe is like now, a glowing wall of itself. And the strangest part is that it stays this way for far longer than the first few minutes of nucleosynthesis. Those early nuclei formed quickly, minutes. But this fog lasts hundreds of thousands of years. For a long time, the universe is old enough to have chemistry's building blocks, but too hot to be chemistry. It has nuclei, but not atoms, because atoms require a delicate agreement. They require electrons to slow down enough to be captured, to settle into stable patterns around nuclei, rather than rushing past like wind. But in the cosmic fog, electrons are too energetic. Every time an electron gets close to a nucleus, a passing photon has enough punch to knock it free again. The universe is not calm enough to allow neutral atoms to endure, so the cosmos waits. It expands, and as it expands, it cools. The temperature falls, not because the universe is losing energy to some outside space, but because the same energy is being stretched across a larger and larger volume. The radiation bath cools as the universe grows, like a note falling lower as a string loosens. And while this is happening, something else is quietly becoming possible. The universe is not perfectly smooth. It never was. Even in the fog, there are tiny differences, slight variations in density, almost unimaginably small. Some regions have just a little more matter than others. Some have just a little less. Not enough yet to look like structure, but enough to be a promise. Gravity is already present, already patient, already working in the background. It doesn't need light to travel freely. It doesn't need atoms to form. It only needs mass and time, and it has both. So while the universe appears featureless and opaque, the earliest blueprint of the future is quietly written into it, not in ink. In tiny statistical ripples, variations so small that later we'll describe them as 1 part in 100,000. The fog hides these ripples from any eye, but it does not erase them. If anything, the fog preserves them, like a sealed room holding a delicate arrangement intact. And if you let yourself think about that for a moment, it becomes almost surreal. For hundreds of thousands of years, the universe is bright, but blind, full of matter, but unshaped, full of light, but unable to send it cleanly across distance. And all of it is moving toward a single quiet turning point. Because what ends the fog is not a sudden explosion or a dramatic collision. What ends it is something gentle, cooling, A slow drop in temperature until the universe crosses a threshold where electrons finally begin to behave differently. Not because they've been forced, but because the conditions have changed enough for a new kind of stability to become possible. It's like watching steam condense, not in one dramatic instant, but in a gradual settling. One moment the air is too hot for droplets to survive, and then, very softly, it isn't. And somewhere in that slow shift, the universe approaches the moment when a proton can hold on to an electron without immediately losing it. When a helium nucleus can wear electrons like a quiet coat. When neutral atoms, the simplest structures of matter, can finally exist in a lasting way. But in the fog era itself, we're still in the tense waiting room, still in the charged universe, still in the bright prison of scattering light. And it's worth lingering here, because this is the stage that makes the next moment feel so astonishing. If you jump too quickly from nuclei formed to atoms formed, you miss the emotional physics of it, the long pause where the universe has almost everything it needs, except the calm. And the calm is not just a mood, it's a physical requirement. So imagine it like this. The universe has built the bones of matter, nuclei. It has electrons ready to become the outer structure. It has light everywhere, flooding the space between everything. But it's still too hot, too charged, too restless. So it stays wrapped in its own fog. A bright, humming, opaque sea where every photon is trapped in a constant conversation with free electrons, where distance still doesn't mean visibility. And somewhere deep inside that fog, the oldest light in existence is still bouncing around, waiting for the first moment it can finally travel and carry a message that has been locked away since the earliest times. A message that, when it finally escapes, will become the faint afterglow we still detect today. Not as a metaphor, as a real signal, a whisper that has been traveling ever since the fog lifted. But here, right now, inside the cosmic fog, that whisper hasn't begun its journey yet. It's still trapped in the glowing haze, and the universe is still, in the most literal sense, keeping its first clear picture of itself hidden, until it is cool enough to reveal it. For a long time, the universe is like a bright room with the lights on, and the blinds pulled shut. Photons are everywhere, endless, frantic, ancient photons, yet they can't travel cleanly across space. They're trapped in a constant ricochet, bouncing off free electrons, scattering in every direction, carrying no stable image of anything. And then, slowly, almost imperceptibly, the universe cools into a different rule, not with a bang, not with a sudden switch, with a quiet threshold. This is the moment called recombination, a name that sounds technical, almost too small for what it actually means. Because recombination is the first time the universe becomes transparent, the first time light is allowed to behave like light again, the first time atoms, true, neutral atoms, can exist for more than a heartbeat. It happens roughly 380,000 years after the beginning, give or take, long enough for the early fire to soften, long enough for expansion to stretch the heat thinner, long enough for matter to stop acting like a storm. And what's strange is that, by human standards, 380,000 years feels ancient. Older than cities, older than writing, older than almost everything we associate with history. But by cosmic standards, it's still the opening seconds. It's the universe exhaling for the first time. Here's what has to happen for an atom to be born. A nucleus, just a proton, or a proton-neutron pair, or helium's tight little bundle, needs to capture an electron and hold on to it, not as a planet orbiting a sun, but as a quantum pattern, a set of allowed notes the electron can occupy. Yet earlier, the universe is too hot for that stability. Anytime an electron tries to settle, it gets hit by a photon energetic enough to kick it free again. Imagine trying to build a snowman in a room where the air is still boiling. You can shape the snow for a moment, but the environment refuses to let it stay. So, in the cosmic fog, electrons remain free, and that single fact changes everything. Free electrons are excellent at scattering light. They are tiny charged targets for photons, little speed bumps everywhere. And because the universe is filled with so many of them, photons can't travel far without colliding. Light becomes trapped in a dense, luminous maze. That's why the cosmos is opaque. Then the temperature drops. Not by a little, by a lot. Down toward roughly 3,000 Kelvin. Still hotter than molten metal, still brighter than any furnace you've ever seen, but cool enough for a new kind of calm. Cool enough that the average photon is no longer so violent. Cool enough that an electron can approach a proton and not immediately get ripped away. This is the moment the universe stops being a plasma and starts becoming something like a gas, a neutral gas, the first true chemistry-friendly environment. And it happens everywhere, not as a single synchronized flash, but as a shifting global settling, regions cooling, electrons finding nuclei, photons losing their power to constantly disrupt the union. If you want one simple picture to hold on to, it's this. For hundreds of thousands of years, the universe is charged. Then it becomes neutral. And that neutralization changes the behavior of light so dramatically that it's almost like the universe opens its eyes. Because once electrons bind to nuclei, there are far fewer free charges to scatter photons. The fog begins to lift. Photons that used to bounce and bounce and bounce suddenly find themselves able to travel. Straight, far, uninterrupted. And those photons, some of them, leave the matter for the first time. They escape, not metaphorically, literally. This is the birth of what we now call the cosmic microwave background, the CMB. But don't let the modern word microwave shrink it in your mind. In that era, that radiation is not microwave. It's more like a hot, glowing afterlight, closer to infrared or visible, depending on exactly when you catch it. It only becomes microwave because the universe keeps expanding for billions of years, stretching those wavelengths longer and longer, cooling that light into the faint, chilly whisper we detect today. The CMB is the oldest photograph in existence. Not a picture taken with a camera, but a snapshot recorded in physics. A map of the moment the universe became transparent. It's the afterglow of the fog lifting. And it's one of the most emotionally strange facts in science that you can say out loud. There is light in the sky right now that has been traveling for nearly the entire age of the universe. Light that began moving freely when atoms were first born. Light that has been on its way ever since. If you've ever warmed your hands near a heater and felt invisible warmth on your skin, you've experienced the same category of reality. Radiation you can't see, but that is undeniably there. The universe is still filled with its own ancient warmth. It just cooled down, and recombination is the moment that warmth becomes a message. Because before recombination, photons can't carry clean information over distance. They can't preserve a story of where they came from. They scatter too often. Their path is scrambled. After recombination, light becomes a courier, a messenger. It can travel across enormous distances without being constantly interrupted, which means the universe can finally begin to have an observable face. It can finally begin to form a visible history. Now, inside this moment, there's also a subtle but profound quantum theme, one that fits the deeper mood of this channel. Atoms are not tiny solar systems. If they were, they would fail. In a purely classical picture, an electron orbiting a nucleus would radiate energy and spiral inward, collapsing into the nucleus in an instant. Matter would not be stable. Chemistry wouldn't exist. You wouldn't exist. The fact that atoms can exist at all depends on the strange rule that electrons occupy discrete states, stable patterns, standing waves, allowed levels. It's like the universe doesn't permit every possible slope down. It forces electrons into certain steps. So, when an electron finally joins a proton to form hydrogen, it isn't just captured. It's placed into an allowed quantum arrangement, a stable compromise between attraction and uncertainty. It's one of the quietest miracles in physics. The same quantum weirdness that makes reality feel slippery is also what makes reality hold together. Recombination is where that weirdness becomes practical, where the abstract becomes tangible, where the universe finally earns the right to say, matter can endure. And the first atoms are mostly simple, almost boring in a way if you're expecting variety. Hydrogen dominates, helium is next. Tiny traces of other light elements exist, but the universe is still mostly a two-ingredient recipe. Yet those two ingredients are enough. Because hydrogen is the simplest atom imaginable. One proton, one electron. And simplicity is powerful because it's stable. It can persist. It can drift through space without immediately falling apart. And once you have stable atoms, you can have stable gas clouds. You can have regions of matter that cool further, clump, and respond to gravity in a new way. You can begin a slow process of gathering, but don't rush past the emotional weight of what just happened. For the first time, the universe has changed its relationship with light. Before recombination, light is trapped inside matter like a restless thought. After recombination, light is released into space as a traveler. So, in a real sense, recombination is a kind of cosmic separation. Light and matter part ways. Matter keeps most of the mass, the inertia, the potential for complexity. Light carries away the memory of the early universe in its pattern. And those patterns matter. The CMB isn't perfectly uniform. It contains tiny fluctuations, faint variations in temperature and density, little hills and valleys in the afterglow. Those variations are unbelievably small, on the order of 1 part in 100,000, but they are everything. Because those slight differences are the first visible fingerprints of structure, the earliest suggestion that some regions are just a little denser than others, that some parts of the universe are ever so slightly heavier, ever so slightly more crowded with matter. And if you give gravity even a tiny advantage, if one region has just a little extra mass, gravity will keep working it, quietly, relentlessly, with no impatience. Recombination doesn't create stars. It doesn't create planets. It doesn't create you. What it does is unlock the conditions that make those futures possible. It turns the universe into a place where matter can settle without being constantly reset by heat and radiation. It allows the cosmos to cool into long-term behavior, and it allows the first true shadows to exist. That last point sounds poetic, but it's literal. Before recombination, there's no clean line of sight. There are no distant lamps, no darkness behind objects, no crisp silhouettes. After recombination, photons can finally travel far enough that illumination becomes meaningful. Light can come from somewhere and reach somewhere else without being instantly scrambled. The universe can begin to have distance in a visual sense. And with that, it can begin to have an atmosphere of space, vastness, separation, emptiness. The fog lifts and suddenly the universe is enormous. Not because it grew in that moment, it's been expanding the whole time, but because now enormous can be experienced. Now, there can be long lines across the cosmic ocean that light can cross without interruption. And there's something quietly personal about that, because the atoms that form in recombination, especially hydrogen, are still here. Not metaphorically still here, actually here. Hydrogen in your water, hydrogen in your cells, hydrogen in the fats and proteins that make up your body. Hydrogen that, for a long time, could not exist as an atom, could only exist as a bare nucleus and a free electron. And then, once the universe cooled enough, that first handshake became possible. A proton held onto an electron, a neutral atom formed, and the story of chemistry began. It's easy to think of atoms as ordinary, like background wallpaper in reality. But in this moment, atoms are new, a brand new kind of object in the universe, a new level of organization. The first stable letters in a cosmic alphabet that will eventually write molecules, then cells, then minds. And while the universe is still mostly quiet and dark, while there are no stars yet, no galaxies, no glowing spirals, the stage has changed. The rules have changed. The conditions have softened. The universe has become transparent. And from this point forward, something very patient can finally get to work in a way it couldn't before. Because when light is no longer trapped and matter is no longer trapped in a hot plasma, gravity can begin to sculpt the neutral gas, slowly gathering it, gently deepening the slight differences, turning tiny ripples into long threads. Not quickly, not dramatically, but in a way that never stops. And if you let that idea sit with you, just for a breath, you can feel how recombination is both a scientific event and a quiet turning of the page. The universe hasn't built the grand structures yet, but it has built the conditions where grand structures become inevitable. Atoms are born, light is set free, and the cosmos becomes a place where complexity can finally begin to accumulate, instead of constantly being erased by heat. When the universe finally becomes transparent, it feels, at least in the storybook sense, like the moment a curtain lifts. Light is no longer trapped in constant collisions. Atoms can hold together. Space can stretch and cool without instantly tearing everything apart again. And in that quiet clearing, something ancient and patient takes the stage without ever announcing itself. Gravity. Not the dramatic movie version gravity that yanks objects downward like a hook. This is gravity as a slow preference. A gentle vote cast again and again for together instead of apart. Because even in that newly calm universe, matter isn't perfectly smooth. It never was. If you could zoom out and see the early cosmos right after recombination, you wouldn't see a blank, uniform mist. You'd see a nearly uniform mist, almost perfectly even, yet not quite. The difference is tiny, about 1 part in 100,000, a faint unevenness, a subtle grain, the kind of imperfection you'd never notice in a casual glance. But gravity notices. Gravity doesn't need drama. Gravity only needs a slight imbalance and time. A little more matter here than there, a small dip in density, a small bump. And once those bumps exist, gravity begins doing what it does best, without hurry, without fatigue, without changing its mind. It leans into the bumps. It deepens the dips. It takes the tiniest advantages and turns them into a destiny. This is one of the strangest emotional truths in cosmology. The universe becomes structured not because something pushes matter into place, but because matter quietly falls into itself. If you've ever watched dust gather along the edges of a room, always finding corners, always finding low points, you've seen a gentle analog of this process. The room doesn't command the dust. The dust simply responds to the shape of the space and the little currents you can't see. Now imagine a universe-sized room. Imagine a universe-sized dust. Gravity is the corner. Gravity is the low point. Gravity is the quiet rule that says, if you're slightly heavier than your surroundings, you will become a little heavier still. And the early universe is filled with hydrogen and helium, simple atoms drifting like a thin, invisible fog. No stars, no galaxies, no bright beacons. Just a vast neutral gas, cooling, expanding, and carrying within it those tiny density ripples. So, the story shifts from can atoms exist to something even more patient. Can atoms gather? Because gathering is the beginning of everything else. When a region is slightly denser, it has slightly more gravitational pull. That means it draws in nearby atoms, just a little. And as it draws them in, it becomes denser still, so it pulls a little harder. It's a feedback loop made of calm. Over time, that region becomes a cloud. Not a cloud like the ones in a blue sky, because there's no blue sky yet. No air, no sunlight, no weather. This is a cold, dark cloud of hydrogen and helium, drifting through expanding space, slowly thickening like a thought that keeps returning. And as matter gathers, something else happens, something that seems almost like the universe discovering friction. As atoms fall inward, gravitational energy turns into heat. Falling is not free. In the deep sense, falling is a way of converting potential into warmth. So, these growing clouds begin to warm in their densest centers. The universe is still overall cooling, but locally, inside collapsing pockets, temperatures can rise. That's the paradoxical beauty of gravity. It can make cold space produce hot centers. And this is where the universe begins to look less like a featureless ocean and more like a map of currents. Because collapse doesn't happen everywhere at once. It happens where the ripples are slightly higher, where matter is slightly more willing to gather. Over millions of years, those gathering places connect like threads. Not straight lines, more like branching river systems. This is the beginning of what we call the cosmic web. A network of filaments and knots, long tendrils of matter stretching across immense distances, with denser nodes where future galaxies will form. and emptier voids where not much gathers at all. If you want a gentle mental image, imagine foam. Bubbles pressed together, with thin walls between them. Now, replace the bubble walls with filaments of gas and dark matter, and replace the bubbles with vast empty regions. Because yes, beneath this visible gas, there is something else shaping the architecture. A scaffolding we don't see directly, but we see its fingerprints everywhere. Dark matter. In this story, dark matter is not a monster. It's not a magical substance. It's simply an unseen kind of mass that responds to gravity and adds gravity to the universe's accounting. It doesn't interact with light in the same way atoms do. It doesn't form atoms. It doesn't glow. It doesn't scatter photons. So it can start clumping even earlier, providing gravitational wells that ordinary matter falls into later. Like invisible valleys in the landscape. The hydrogen and helium don't need to know what dark matter is. They don't need to touch it. They only need to follow the slope of gravity. And over time, they do. Now, there's a fragile detail here that makes the story feel even more alive. Even after recombination, the universe isn't perfectly neutral forever. As matter collapses and heats, some regions begin to ionize again. Electrons knocked free locally by heat, by shocks, by energetic processes. Not the whole universe returning to plasma, just patches, pockets, localized sparks in an otherwise dark ocean. It's as if the universe, after finally becoming calm enough to build atoms, begins to rehearse the conditions that will later ignite stars. A cloud gathers. It compresses. It warms. If it warms enough, it can strip electrons again, making the gas more reactive, more able to cool in certain ways, more able to collapse further. The details get technical quickly, but the feeling is simple. Gravity is teaching matter how to concentrate. And concentration is the key, because you don't get stars from diffuse gas. You get stars from gas that has been persuaded over and over to become dense. Now, as these clouds grow, there's a constant tug of war. Expansion is still happening, space is still stretching, trying to thin everything out. Gravity is trying to gather, and in many places, expansion wins. Matter stays thin, it drifts. It never becomes anything dramatic. But in some places, where the initial ripples were just a little stronger, where the local gravity wells were just a little deeper, gravity begins to win. And when gravity wins, it doesn't win loudly. It wins through persistence. It wins the way a slow leak wins. It wins the way time wins. Atoms drift inward, more atoms follow. A cloud becomes thicker, the center becomes denser, the center becomes warmer. And here's an important sleepy kind of truth. Nothing in this era happens fast. The universe is learning how to build in slow motion. There are no sudden miracles, just long, steady pressure. And yet, despite the gentleness, this is one of the most consequential stretches of time in cosmic history, because it is where randomness becomes geography, where small differences turn into large-scale structure, where the universe stops being almost the same everywhere and starts being different in different places. You can almost feel the universe becoming a world with neighborhoods. Filaments where matter gathers. Voids where matter thins. Knots where gravity pulls hardest. If the universe had a heartbeat, this would be the period where it slows down enough for patterns to persist. Now picture one of those dense knots, a region where hydrogen and helium have been falling inward for a long time. The center is denser than the edges. The pressure increases. Collisions become more frequent. The gas warms. At this stage, the cloud is still dark. There's no light source inside it. It's like a mountain of invisible air in a universe without sunlight. But the physics is changing in one direction only. Compression, heating, density, pressure, all of it creeping upward. Gravity doesn't care about aesthetics. Gravity cares about mass. And mass, given time, will gather. Eventually, the center becomes so dense that the temperature climbs into a range that feels almost impossible compared to the cold background of space. And this is where the story begins to approach an edge where a cloud is no longer just a cloud. Because if the core can become hot enough, millions of degrees, then a new process can begin. A process that doesn't just release light, a process that creates it, fusion. But before that ignition happens, it's worth pausing on the character of gravity itself, because it's easy to underestimate what it's doing here. Gravity is not just pulling things together. Gravity is selecting the future. It is turning the universe into a place with structure, meaning that later, when stars finally appear, they will not appear randomly scattered like lonely candles. They will appear along the filaments, in clusters, in the knots where gravity has been quietly hoarding matter for eons. Gravity is building the stage before the actors arrive, and it does it in the most sleepy way imaginable, slowly, steadily, without ever changing its tone. So, if you're listening tonight, and you let your mind relax into that image, you can feel the scale of it. A universe full of new atoms, an enormous darkness, tiny ripples, only 1 part in 100,000, slowly amplified into rivers of matter stretching across cosmic distances. Invisible scaffolding shaping the flow, hydrogen and helium drifting like a soft snowfall into gravitational valleys. And in certain places, the centers of those clouds are becoming warm enough that the universe is about to do something it has never done before. Not just form atoms, not just free light, but create a brand new light source from within matter itself. A first ignition that will change the meaning of darkness forever. For a long time, the universe is doing something that feels almost like holding its breath. Not in a dramatic way, more in the way a winter field holds still before the first thaw. Hydrogen and helium drift through a darkness so wide, it's hard to picture. There are no lamps, no suns, no galaxies with glittering arms. Just the slow architecture of gravity and the quiet gathering of gas. And inside some of those gathered clouds, the same story repeats again and again. A little more matter, a little more pull, a little more inward drift. The centers grow denser. Denser becomes warmer. Warmer becomes restless. If you could stand inside one of those collapsing clouds, if that word even makes sense in a universe without solid ground, you wouldn't hear anything. You wouldn't see anything, but you would feel pressure building like invisible weather. Atom meets atom. Collisions become more frequent. The gas begins to behave less like a thin mist and more like something with weight. Gravity, patient as ever, keeps tightening its gentle grip. And then, eventually, the cloud reaches a threshold where the universe is no longer just gathering matter. It is preparing a fire. At first, it's just heat. Heat born from falling. As gas drops deeper into its own gravitational well, it gives up potential energy and turns it into temperature. The center becomes a hidden furnace, still wrapped in darkness, still not shining, but undeniably warming. This is one of the strange rules of cosmic life. In a cold universe, gravity can make hot places, and it doesn't stop at warm. It pushes toward a number that sounds almost absurd compared to the chill of space, around 10 million degrees in the core. 10 million. Not because the universe likes big numbers, but because physics demands it. At lower temperatures, hydrogen nuclei move too slowly, too politely. They approach one another, and then, because they are both positively charged, they repel, like two magnets refusing to touch. But at about 10 million degrees, the collisions become fierce enough that something rare can start to happen. Hydrogen nuclei can get close enough for the next barrier to matter. Not just the electric repulsion, but the strong force, the deep glue of the nucleus that only works at unimaginably tiny distances. When two protons finally get close enough to feel that strong force, the rules of reality change in an instant. They stop behaving like strangers passing in the night. They begin to bind. This is fusion, but not the cartoon version. Not a sudden explosion. Not a cinematic blast of light. Fusion at first is quiet, stubborn, and slow, like a match that refuses to catch until it's held in exactly the right way. Two protons meet. One of them changes identity through the weak interaction, becoming a neutron. And that tiny transformation is what allows the first stable step forward. A new nucleus appears, deuterium, hydrogen with a heavier heart. From there, the chain continues. Deuterium can fuse again, building helium in stages. Energy is released in small, consistent payments. And the universe, after ages of darkness, finally has a new kind of engine. Not gravity alone, but gravity feeding a nuclear fire. What makes this moment feel almost magical is that it's not merely heat being produced, it's light being born, photons created inside the core, trying to escape. But even now, the newborn star isn't instantly a bright point in a clear sky. The surrounding gas is thick. The photons collide again and again on their way out, like someone trying to leave a crowded theater while every seat is occupied. So, the first light takes time. It fights its way outward through a maze of hot plasma and dense matter. It is trapped, scattered, delayed. Yet it keeps going, because that's what light does. And while photons are struggling outward, the star is discovering its balance. Because gravity doesn't stop pulling just because fusion begins. If anything, gravity pulls harder as the core becomes denser. So, there's a tug-of-war now. Gravity wants collapse. Fusion wants expansion, because heating the gas increases pressure, and pressure pushes back. This is the first great self-regulating system in the universe. If gravity squeezes the core tighter, the temperature rises. If the temperature rises, fusion speeds up. If fusion speeds up, energy output rises. If energy output rises, pressure rises. And that pressure pushes outward, resisting gravity's squeeze. It's a cosmic thermostat, and it's astonishingly stable. Not perfectly stable. Stars can evolve, swell, flicker, and die, but stable enough to burn for a long time. And this balance is written right into the star's posture, like a steady breath. Gravity pressing inward, pressure pressing outward, the whole object hovering between collapse and escape. This is the moment when matter stops being merely stuff. Matter becomes a living process. And somewhere, at last, the darkness breaks. A first star truly turns on. It's worth appreciating how strange this is. The universe went from having no lights at all to having a light that can be seen across unimaginable distances. A bright point in the deep, like a lantern hung in an endless night. These earliest stars are not gentle little suns. They are likely massive, built from mostly hydrogen and helium, without heavier elements to help the gas cool and fragment into smaller pieces. Without those cooling pathways, clouds can collapse into larger, heavier cores. So, the first generation of stars, often called population 3 stars, may have been giants, hotter, brighter, short-lived. They burn through their fuel with urgency. They pour out ultraviolet light that can tear electrons free again, ionizing the surrounding gas. So, in a quiet way, the first stars begin to change the universe's mood. The neutral fog that once made the cosmos transparent starts to be locally undone in patches, not because the universe returns to chaos, but because starlight is powerful enough to rewrite the charged state of matter nearby. The first stars don't just shine, they sculpt. Their radiation pushes, heats, ionizes, their gravity gathers, their winds stir. Their eventual deaths will seed space with new ingredients. And now the story gains a kind of emotional weight, because this is the moment when the universe stops being a nearly featureless expanse and becomes a place where events can happen. Because once you have stars, you have warmth in cold space, chemistry on dust and gas, light that can travel, energy that can build complexity. And if you pull the camera far, far back, you can see it as a change in rhythm. For hundreds of thousands of years after recombination, the universe is mostly quiet and uniform, slowly cooling, slowly gathering. Then stars ignite, and suddenly the cosmos has punctuation marks, bright points, bursts, a beginning of here and there, a beginning of history that leaves visible traces. And this is where the breath you're taking right now becomes part of the story again. Because the atoms in your body did not just appear. They were processed, refined, changed by these stellar furnaces. The hydrogen in the water you drink carries the memory of the early universe, yes, but the carbon in your cells, the oxygen you rely on, the calcium in your bones, those require stars to exist. So, when the first stars ignite, it's not only a beautiful cosmic scene, it's the universe taking its first real step toward you. Toward chemistry with more letters in its alphabet, toward a periodic table that becomes a storybook, toward matter that can be arranged into planets, oceans, lungs, and thoughts. And even though the first stars may have been brief, burning fast, shining fiercely, what they start is permanent in one crucial sense. They turn the universe into a factory for new elements, a place where simple atoms can be transformed into richer ones, layer by layer. So if you imagine that first ignition tonight, try to picture it not as a single flash, but as a slow awakening. A collapsing cloud, dark and heavy, reaching its tipping point. A core heating toward 10 million degrees. 2 protons finally getting close enough to bind. A trickle of fusion becoming a steady burn. Pressure rising to meet gravity. All light beginning its long journey outward. And then, finally, an ancient darkness receiving its first sunrise. From here on, the universe won't just have atoms. It will have furnaces that can rewrite atoms into something more. Inside a star, time feels different. Out here, on Earth, an afternoon can pass in the space between 2 sips of coffee. But in a stellar core, an afternoon isn't measured by clocks. It's measured by collisions, by pressure, by heat, by the steady, patient work of turning one kind of nucleus into another. For a while, after a star ignites, the main job is simple. Fuse hydrogen into helium. That's the clean, reliable engine that keeps the star from collapsing under its own weight. It's the long, steady middle of a star's life. But helium is not an endpoint. It's a kind of pause. Because helium nuclei, 2 protons and 2 neutrons, are unusually stable. They sit there like tightly packed stones. And that stability is both a blessing and a barrier. It takes real effort to push past it. So as the star ages, it slowly changes shape from the inside out. Its core becomes richer in helium, ash, and hydrogen burning shifts outward into a shell. The core contracts under gravity, and when something contracts, it heats. Gravity returns to do what it always does. Squeeze until a new rule becomes relevant. And eventually, in the deep center, helium becomes hot enough to stop being comfortable. This is where the story begins to feel like the universe is learning a new alphabet. Helium nuclei are sometimes called alpha particles. And the next step, one of the most beautiful coincidences in all of physics, is called the triple alpha process. That name sounds technical, but the idea is almost poetic. 3 helium nuclei find a way to become 1 carbon nucleus. And the surprising part is that it's not supposed to be easy. Helium nuclei repel each other. They don't want to merge. And even when 2 helium nuclei do manage to stick together briefly, the intermediate nucleus, beryllium-8, is unstable. It falls apart almost immediately, like a sandcastle collapsing as soon as it's shaped. So, how do you ever build carbon if the stepping stone crumbles? The answer is, you do it in a place where there are so many collisions, so much pressure, and so much heat that the universe gets a second chance before the first chance disappears. Inside the helium-burning core of a star, beryllium-8 can form for a fleeting moment. And in that fleeting moment, a 3rd helium nucleus can collide and snap into place. 3 become 1, and carbon is born, not as a metaphor, not as a symbol, as an actual nucleus, 6 protons, 6 neutrons, something the early universe could not manufacture in bulk, something Big Bang nucleosynthesis never had time or conditions to produce. Carbon is a star-made element, which means that every carbon atom in your body has a history that includes a stellar core. Your fingertips, your skin, the soft tissue around your eyes. All of it carries a signature of this process. And once carbon exists, the universe can finally start buildings, like it has a toolbox instead of just raw material. Because carbon is not only important for life, carbon is important for physics. It's one of the first elements that allows more complex nuclear reactions inside stars. It opens doors. From carbon, the core can forge oxygen by fusing carbon with another helium nucleus. Carbon plus helium becomes oxygen. Oxygen plus helium can become neon. And in the most massive stars, the chain continues into heavier and heavier nuclei. Each step requires higher temperatures, because heavier nuclei have more protons, and more protons means stronger electric repulsion. the star has to squeeze harder and burn hotter to keep forcing nuclei close enough to fuse. So, the star becomes a layered world. Different fuels burning in different shells, like nested furnaces, hydrogen burning in an outer shell, helium burning deeper in, carbon burning deeper still in the biggest stars, then neon burning, then oxygen burning, then silicon burning. It sounds like a menu. It's actually a countdown. Because every time you move to a heavier fuel, the burning gets faster and less stable. Hydrogen burning can last for millions or billions of years, depending on the star. Helium burning is shorter. Carbon burning is shorter still. In the most massive stars, the late stages can become shockingly brief. Thousands of years, even days for the final steps. The closer you get to the end, the more frantic the furnace becomes. And yet, even in that urgency, there's a hard boundary the universe refuses to cross inside a living star. That boundary is iron. Iron is the dead end, the cliff edge. It's not that iron is forbidden. It's that iron sits at a special point in nuclear physics where you stop earning energy by fusing nuclei together. Up to iron, fusion releases energy. It's profitable. It's like combining blocks and getting paid in heat and light. But iron is different. Iron is already too tightly bound. To fuse iron into something heavier, you have to spend energy rather than gain it. It's like trying to build a fire by adding cold stones. The fire doesn't grow, it weakens. So inside a massive star, silicon burning can assemble nuclei that climb toward iron and nickel. The core gradually fills with these iron group elements, dense, inert ash that no longer helps hold gravity at bay. And that's the quiet horror hidden inside the beauty of starlight. A star can manufacture its own collapse. The very process that made the star shine, fusion, eventually creates a core that cannot fuse its way out of trouble. When enough of the core becomes iron, the star loses its most important defense. Gravity has been waiting the whole time, and now it doesn't have to wait anymore. This is why stellar nucleosynthesis feels like a story with two hearts. One heart is gentle and generous, stars making carbon and oxygen, filling the universe with the ingredients of chemistry and oceans and lungs. The other heart is ruthless. Every new element is a step closer to a point where the star can't keep itself up. But before that ending arrives, and this matters for us, stellar nucleosynthesis is the reason the periodic table is more than a list. Without stars, the universe would be mostly hydrogen and helium forever, with tiny traces of lithium. That's it. No oxygen to breathe, no carbon chains, no nitrogen in the air, no silicon for rocks, no iron for blood. Stars are not just lights. They are element factories. They are the reason matter can become interesting. And there's something deeply calming about that, if you let it land, because it means complexity is not an accident that happened once. It's a process the universe repeats wherever gravity gathers enough gas, wherever pressure and heat reach the right thresholds, wherever time is long enough for collisions to do their slow work. So tonight, if you want a simple image to carry with you, picture a star not as a ball of flame, but as a layered workshop. In the outer layers, hydrogen still quietly becoming helium. Deeper down, helium fusing into carbon. Deeper still, carbon and oxygen being shaped into heavier cores. All of it wrapped in gravity's steady embrace, like a hand holding a glowing coal. And somewhere, in the middle of that furnace, a carbon nucleus forms, 6 protons settling into a stable arrangement, destined eventually to be scattered into space, destined to become part of a planet, part of an ocean, part of a living cell, part of you. And as that core approaches iron, the star is doing one last intimate act. It's making the final ingredients that will matter when it can't hold itself together anymore. Because once iron arrives, the story stops being about slow burning. It becomes about what happens when a cosmic furnace reaches the point where fuel no longer pays the rent. A supernova isn't just an explosion, it's a decision. For millions of years, a massive star holds itself up the same way you hold a heavy box on a shelf, by constantly pushing back. Gravity presses inward, fusion pushes outward. a quiet balance, a steady glow. But deep inside, the star has been keeping a secret. It can't do this forever. As heavier elements build up in the core, the star eventually creates a center made of iron, dense, stubborn, and strangely unhelpful. Iron doesn't pay the star back with energy the way lighter fusion does. Adding iron to the core is like adding bricks to a bridge that's already at its limit. The weight increases, but the support doesn't. And then, at some moment that could be happening right now somewhere in the Milky Way, the core reaches a tipping point. Gravity stops negotiating. The iron core collapses in on itself so fast, it's hard to compare it to anything in everyday life, except maybe the feeling of a floor suddenly disappearing under your feet. Except this floor is a sphere of matter larger than Earth, falling inward at a fraction of the speed of light. In the final seconds, the star's center compresses until the physics becomes extreme. Electrons are shoved into protons, producing neutrons and a flood of ghostly particles called neutrinos. The core becomes something unimaginably dense, neutron-rich, compact, and fierce. And then the collapse rebounds. Not gently. A shockwave forms and races outward through the star's layers, like a cosmic heartbeat that's too strong for the body to contain. In that instant, the star's outer material is no longer held by gravity's grip. It's thrown outward into space, an expanding shell of hot gas and ash, moving faster and faster as it escapes. For a brief time, a single star can outshine an entire galaxy. That's not a poetic exaggeration. It's a real scale of brightness. Imagine every light in every house in every city on Earth turning on at once, and still being invisible beside that flare. But the real miracle isn't the light. The miracle is what the shockwave does on its way out. Because in that violence, inside that rushing front of heat and pressure, atomic nuclei are bombarded by neutrons so quickly that the usual slow steps of element building get skipped. It's like taking a staircase, but suddenly the building catches fire and you start leaping floors at a time. This is one of the pathways that makes the heaviest elements, gold, platinum, uranium, atoms that require more than a patient, steady furnace. They require urgency. They require chaos. So, when you've ever held a piece of jewelry in your hand or seen a gold ring flash in sunlight, you were looking at matter that likely needed a star to die violently to exist at all. And then comes the part that matters most for you. The supernova doesn't keep its treasure, it scatters it. Everything the star built, carbon, oxygen, neon, silicon, and the heavy elements forged in those final moments, gets blasted into the galaxy. The ingredients don't stay locked in the grave of the star. They're flung outward, seeded into interstellar space, mixed into the thin, cold darkness between stars. This is the moment the universe learns how to share, because without this scattering, the story would be small and local. Elements would remain trapped in stellar interiors, never making planets, never making oceans, never making bones. Instead, the galaxy becomes enriched. Each supernova is like a painter flicking a brush across a black canvas. Tiny grains of dust, atoms and molecules, drifting outward and cooling, spreading out over light years. And if you stay with that picture for a moment, you can almost feel how patient the next phase is going to be. After the flash, after the shockwave, after the bright spectacle fades, those atoms don't rush. They drift, they cool. They gather slowly in the dark, where the temperature drops and chemistry begins to whisper again, quietly, gently, on the surfaces of dust grains that float like soot in starlight. And by the time this story reaches your glass of water, those scattered atoms will have learned how to become calm. After a supernova, you might expect the universe to feel loud for a long time, but it doesn't. The brightness fades, the shockwave runs out of things to crash into, and the galaxy returns to its usual habit, quiet, thin, and cold. In most places, space is emptier than any vacuum you could make on Earth. The temperature hovers just a few degrees above absolute zero. And yet, this is where the gentlest kind of chemistry begins. Because the explosion didn't only throw atoms outward, it threw seeds. Tiny grains of dust, made from carbon compounds, silicates, frozen metals, drift through the dark like microscopic ships. You can picture them as ash in a beam of sunlight, except the beam is starlight, and the room is a spiral arm of the Milky Way. Over time, gravity gathers those seeds into places where the emptiness becomes less empty, regions where gas is slightly thicker than normal, still far thinner than Earth's air, but thick enough that atoms begin to meet each other more often, thick enough that the galaxy can start collecting itself. These are molecular clouds. They're enormous, so large that a single cloud can stretch across dozens, even hundreds of light years. If one floated through our solar system, it would swallow the distance between stars like fog swallowing streetlights. But inside, the mood is strangely calm. The cloud is cold and dim. It blocks harsh radiation. It gives atoms a sheltered place to slow down. And slowing down is everything. In the hot early universe, matter moved too fast to settle into relationships. In the violence of a supernova, nothing can hold still. But here, in the dark interiors of these clouds, motion becomes a whisper. Collisions become soft taps. And when an atom finally sticks to a dust grain, it can linger long enough for the next step to happen. Dust grains become little laboratories. A hydrogen atom lands, then another. They meet and, with the surface helping to carry away energy, they stay together as H2, molecular hydrogen, the simplest molecule, and the quiet backbone of future stars. Oxygen drifts by, carbon follows, nitrogen. Simple combinations form: carbon monoxide, ammonia, methane. And with the right encounters in the right cold corners, something deeply familiar begins to appear: water. Not oceans, not rivers, not even droplets. Just the earliest hints: H and O meeting on a grain of dust, forming H2O, then freezing into a thin film of ice that coats that grain like frost on a window. A delicate chemistry written in layers, atom by atom, over time scales so long they barely feel like time at all. And the atoms themselves are patient travelers. One carbon atom might drift through interstellar space for thousands, sometimes millions of years without becoming part of anything permanent. It can float alone, carried by gentle pressure from starlight, nudged by magnetic fields, slowly wandering through the galaxy like a leaf in a vast invisible breeze. But the galaxy is persistent. Clouds collide, densities rise. Gravity finds the heavier pockets and tightens its grip. Somewhere inside the cold dark, a region begins to contract. Not dramatically, not at first, just a slow gathering, a subtle inward lean. And when enough material collects, the quiet chemistry of the cloud becomes the beginning of a much larger story. Because these clouds don't stay clouds forever. They become nurseries, places where new stars will ignite and new solar systems will assemble. Places where those scattered elements finally stop wandering and start taking shape into rock, into air, into water, and eventually into you. Tonight, you don't need to understand every detail to feel the weight of it. Just notice something simple: your breath moving in and out, the quiet warmth in your chest, the steady presence of your body resting here in the dark. Because hidden inside that ordinary calm is a story that began before there were names for anything. The hydrogen in the water you drank today is ancient, so old it has barely changed since the universe first cooled enough to let matter settle. The carbon that shapes your skin and muscles was once made in the deep, steady heart of a star that burned for millions of years, patiently turning simpler things into something more. And the iron in your blood, the iron that carries oxygen through you right now, was not born gently. It arrived through endings, collapsing stellar cores and explosions that scattered new elements into the dark like seeds. So, when you look at a glass of water, or feel your heartbeat, you're not just looking at your life. You're looking at cosmic history arranged into a human moment. And maybe that's the softest kind of wonder, knowing you're not separate from the universe, but made of it. A brief, beautiful pattern of atoms that traveled through time, through cold clouds and bright stars, through silence and fire, and somehow arrived here as you. If you're listening right now, I'd love to know where you are in the world and what time it is for you. Drop it in the comments. I read them, and it's always comforting to see how many quiet places this channel reaches at night. And if this story helped you feel calmer, if you'd like more gentle science you can fall asleep to, consider leaving a like and subscribing to The Quantum Slumber. It's a small thing, but it helps these videos find the people who need them most. For now, you can let your mind loosen its grip on the day. Let your breathing slow, let your shoulders soften, and let the universe keep its oldest promise, to cool, to settle, to become quiet. Good night, and sweet dreams, fellow stardust.